So let's look at half-life now. Half-life is a property of a radioactive material. We define it, the half-life of a radioactive nuclide, group of nucleuses, or a mass of an element that's radioactive, and we define the half-life as the time taken for half of any sample of unstable nuclei to decay. Okay, so this is again reference to decay, which is a naturally occurring spontaneous event, and the time it takes for half of it to become stable again, right? So you've got a kilo of an unstable radioactive substance. It's the time it will take for half of that to become stable and to become a stable element. It will be completely transformed into something else that's no longer radioactive. Now, the time, the half-life, can span mere seconds or fractions of a second to a ridiculous amount of time, such as this half-life here, which is 4.5 times 10 to the power of 9 years. Half-life and the length of it basically decides which kind of radioactive material you would choose for something like tracing in the human body for medical purposes. You would want to use a half-life which is measurable, that's not going to go down too quickly so that you can have a constant reading. But if you're using it for nuclear fuel, you don't want a half-life that you're going to have to take into consideration for the following millennia, right? Because basically nuclear waste has to be kept safe, and that causes considerable economic pressure on for government. So you do need a half-life that's not considerable. Unfortunately, in terms of nuclear waste, the half-life of nuclear waste is extremely long, and we do have economic issues with that. But anyway, we'll talk about that in topic 8. Half-life, there's your definition, and yes, you do need to learn it off by heart. Now, how does this radioactive half-life, how do we look at it, how do we calculate it? For that, we need a decay graph. And I'm going to ask you to have a look at this simulation. If you go to the link on the slide here, it will take you to this simulation, and it will allow you to manipulate the half-life of a radioactive material. This is a nice representation. So basically, this would be a mass of a radioactive element, so a kilo of uranium-238, for example. And we're going to choose a large half-life, and what this will do is simulate the emission situation. So the dots will change color to represent an emission of a radioactive emission of alpha or beta. So this blue dot represents a nucleus which has lost an alpha or a beta or a gamma and has now become stable, right? So what this graph now is representing is the percentage of undecayed nuclei. How many are left, right? So this is a plot of the red dots, the undecayed nuclei. And we can see here that the number of undecayed nuclei is decreasing exponentially. So if we continue to play, we can see that we get this curve, which is exponential. Now, in high level, what we'll do is we'll look at that exponential equation and we'll do some analysis of it. But for now, the only thing you need is to be able to draw a graph like this one and understand it. So here we have a graph of percentage of undecayed nuclei. What are we looking for in terms of half-life? We are looking for the time for 50% to be left. So we would look here at where the percentage has gone down by half, and we would measure and see that the half-life is approximately 30 seconds. And the key thing with an exponential graph is that that pattern repeats itself. So if we now go from 50 to 25, it should take the same amount of time for it to halve again. So if we go from 30, it should take us approximately to 60 exactly. So every time the percentage goes down by half, you should have a half-life of 30. Okay, and we could do a small one, see if that makes a difference. You can see that's a small half-life there. What's happening is that each individual atom is decaying quickly, much faster, and we're getting a half-life, we go down to 50, which is approximately about 12 seconds, for this undecayed nuclei. Now, this little red dot here is still red, and this is really, really nice because it illustrates this idea of randomness. Previously, we talked about the nature of decay being spontaneous and random. And what that means is that although we can say for sure that half of all these atoms will decay in a half-life, definitely, right? What we cannot do is say exactly when this one will decay. And that's the nature of random radioactive decay, this lack of predictability on an individual level. But the fact is, we can make massive predictions in terms of a large number of them. Now, these graphs don't all have to look the same. There are a number of different quantities that we can put on the y-axis for a decay graph. We can put count rate, which is basically the number of particles emitted using a GM tube, like the one in the video in the previous explanation. So number of clicks, number of emissions, that will definitely be something you could see on a y-axis. And again, the pattern is exactly the same. The number of count rates will go down by half as well. So you will go from 50 to 25, and then it gives you a half-life of, on here you can see, approximately 50 seconds. So that's another one. And count rate is actually proportional to activity. So the more radioactive something is, the more emissions it will give off. But actually that relationship we will look at in high level. You can also have activity in becquerels. We mentioned that previously. Activity would be the number of emissions per second. But the same pattern, it's the same idea and the same pattern in terms of half-life. The time it takes for it to go down by half will give you the half-life. Now, one last issue that comes up, we mentioned background radiation. Occasionally in questions, you must consider the possibility of there being background counts in a half-life curve like this one. So this would be a count rate for a radioactive material, not including background radiation. Occasionally, you will see a half-life graph which is slightly skewed. That means there's an extra. Always take into consideration for IB questions the possibility that they will ask you the effect of the effect of background radiation on a graph like this one, and basically that will add an extra constant quantity throughout the whole graph. Background radiation is even and constant, and it always has the same magnitude throughout the time span, so you would have to subtract it. So one of the important things to state is to make half-life graphs accurate and fair, you would discount and remove background radiation. Secondly, you also need to take into consideration all the safety implications when dealing with radioactive substances. I think that should prepare you for all eventualities.